in the second author's doctoral thesis. So here's a plan of my talk. So first, I introduce continuous wavelet transforms in perspectives of group representations. Then we show an application of our result to the analysis of vector-valued vector fields of three-dimensional space. Then after that, we go to the general argument. So let us start the continuous wavelet transforms. I start from the classical Calderon reproducing formula. It is a formula for classical harmonic analysis. So let phi be the square-integrable functions on the real line. Let C phi the quantity defined by this integral. So we assume that C phi is finite, where phi is a Fourier transform of phi. So for non-zero real number A and real number B, we define phi B A in this way. So namely, phi B A is the translation and dilation of function phi. Then the formula says every function f is expressed as a continuous linear combination of phi B A, and the coefficient is obtained by the inner product of f and phi B A this way. And the integral is Hilbert space valued. So we should explain more. So if substituting x, we have this, and if the right hand side converges, this holds. So this is the reproducing formula. And if the function does not converge, in general, the formula means in the weak sense. So then formally, we take the inner product of any vector. We have this, and this formula is always hold, and this whole formula means this formula. And we observe this formula from the perspective of group representation. So let G be the affine transformation group on the real line. So for non-zero A and real number B, BA denotes the affine transform X plus B. And let I, the representation on G, realize naturally on L to R in this way. So phi dBA is just translation by B and dilation by A. And let D mu is a measure on G, defined in this way. This is a left invariant Hall measure. Then the Calderon formula says F is a continuous linear combination of phi dBA phi. And this means that for every F and F theta, the product is equals the integral of inner product like this. And we rewrite this form relation in this way. So let W phi the continuous wavelet transform defined from F to function on G, F to this function, and this is isometry. This means this formula. And in the physician notation, identity operator on L2R is decomposed into this rank 1 operators. So this phi d phi is called coherent state vector. So these formulas are equivalent, and we consider the third type formula. And anyway, so once we have such a group representation perspective, we can generalize to various subgroups and various representations. So actually, we have many previous works developed. So for us, we consider the following setting. So let H be a closed linear subgroup, linearly group of G and R, and let G be the symmetric product of Rn with H. So this acts on Rn by translations and linear transforms. Let sigma be a unitary representation on Cm. Then we consider the Cm valued square integrable function on Rn and its action Z. We define the unitary representation pi in this way. So essentially, this is a translation by G, and so F is a vector-based function, and sigma operator acts on in this way. Then in this setting, under some general assumption, our goal is to find phi that this reproducing formula holds. In our setting, phi is not reducible in most cases. This is somehow specific in our research. So before going to the general argument, I present typical application of our research to the three-dimensional vector field case. So let H be the positive number times SO3. So this is a direct product of group of positive number and group of rotations. Sigma is a natural unitary representation on three-dimensional case. Three-dimensional representation, just taking the rotation part. Let G be the symmetric product of R3 and H. This is the similitude group, namely, so this consists of translation and inversion and rotation. We can consider the natural representation on the space of complex vector fields on R3. Then, applying our result, we can find a special vector fields obtained this way and defined in this way. Then every vector field is a continuous linear combination of phi. Furthermore, if we define the vector fields phi 0 and phi sharp in this way, and then phi equals phi 0 plus phi sharp. And for F, we just guess pi g phi by pi g phi 0 or pi g phi sharp. Then we define F0 and F sharp. And clearly, F equals F0 plus F sharp. But this vector field F0 is curl-free, and the vector field F sharp is divergence-free. In general, it's known that any vector field is decomposed into summation of curl-free vector field and divergence vector field. But our formula exactly gives decomposition. So this is our application. But so we go to the general argument. So let H be a closed linear subgroup of G and R. We denote rho a contour gradient representation. This means so the transpose inverse. Our assumption, first assumption is so this contour gradient action has open orbit. Then we can show that there exists GD1, GD2, and GDK finite number of elements in Rn such that if the OK is the orbit through GDK, so we denote by OK, is open. And if K and L is orbits are disjoint, and the union of such orbit is dense. So anyway, so we have the series of family of open orbits. And for each K, let HK is a stabilizer at ZK. HK acts on CM. So CM is HK module. And we decompose into reducible subspaces, HK invariant subspaces. So we write WK alpha. And let sigma K alpha is a subrepresentation of HK on this WK alpha. So we say that the sigma K alpha and sigma K beta representations are equivalent if exists a unitary operator which defines the action of HK, WK alpha, and WK beta in this way. And the multiplicity of sigma K alpha in sigma is the number of beta that the sigma K beta is equivalent to sigma K alpha. Then the second assumption is for HK stabilizer HK is compact, and the third assumption is the multiplicity is smaller or equal to the dimension WK alpha. So thanks to this assumption 3, we can take unit vector EK alpha in each WK alpha such that if sigma K alpha and sigma K beta are equivalent, then EK beta and UK alpha beta EK alpha, this is the element of K beta. In the product of this vector equal to delta alpha beta. So if alpha and beta is different, then this inner product equal to 0. Related to this formula, we recall the so-called sure orthogonality formula for the representation of compact group HK. So if sigma K alpha and sigma K beta are equivalent, then equivalent, we have B alpha and B W beta. We have such integral of so-called matrix element equals this quantity. And here we have K beta, EK beta, UK alpha beta, EK alpha. Then this equal to 0 if alpha is not equal to beta. So based on this sure orthogonality relation, we can construct our special wavelet transforms. So anyway, for k equal to 1 to k, let HK is a major map such that for Z OK, we have this formula. And C, let's see the function on H, a non-negative function, such that the square of this quantity equal to 1 with respect to the left-hand measure on H. Then we define phi k alpha from C and EK alpha in this way. So actually, so this this converges, and we can show that sigma k alpha is square integrable. And let phi the summation of these phi k alpha. Then our main theorem is that for every f Cm valued square integral function on Rn is a continuous linear combination of phi d phi. So we have this formula where d mu is a left-hand measure on G given by this formula. For the case H is positive times rotation group, and then so there exists one orbit and through 001, and the stabilizer is SO2. And then C3 is decomposed in 3 one-dimensional representations spanned by these unit vector, and this unit vector is a simultaneous eigenvector of SO2. And from these unit vectors, we can construct our continuous Wavelet transform, and then phi 0 is defined from 1, 0, and phi sharp is the summation of y pi 5 plus pi 1 minus 1. Eventually, these are curl-free and divergence-free vector fields. For general 2n plus 1 irreducible representation SO3, we can we can obtain similar construction. So C2n plus 1 is decomposed to one-dimensional sub-representations, and each unit vector we can take concretely unit vector. Then we can construct the continuous Wavelet transform. So the detail is see Oshiro's doctor thesis referred in our abstract. So thank you very much.
Yes, Ishi, you are connected?
Yes.
Yes. We are late today, and we have a constraint at the end of the day due to a cruise boat gala dinner. So it's difficult to ask questions because we have no time. It's not obvious because you are not in presence. So I invite the attendees to send you email. You have your email on your papers, and so if you have questions, I invite you to exchange with Ishi, and I hope he could attend Paris conference for the next time. Okay, thank you, Ishi.